Okay, let's look at today's Leetcoding challenge question, maximum square. We have a 2D binary matrix with zeros and ones. We want to find the largest square containing only ones and return its area. As an example, we have a 4-row 5-columns matrix. The largest square here is the one that's coded in red here. It has 2 rows, 2 columns. So for the square, obviously the number of rows and number of columns is the same. And the area is just the length to the power of 2. So it's 2 to the power of 2 to get 4. And we actually have multiple of that, the largest square. We can just shift this red square towards right by 1 column. We have another one. So this is a pretty straightforward dynamic programming question. So let's say that we have a function called FRC, which takes in a row number, column number. Let's define it as the maximum length for a square, for the squares, with bottom right location at row number, column number there. So as the example, we have an input like this. Let's just randomly tag one row in there and picking another column here. So the function called FRC in our case will be equal to 2. So that's the the square that with the bottom right at this location. The maximum length for the squares is going to be 2 for this location. So let's just assume that we have this function already figured out. Then the original question is asking for the maximum size, maximum area for the squares. So to get to that result using this function is pretty much just going to be maximum of this for row and column in all the possibilities, and have that power squared. So basically we need to populate all the possibilities for the row number and column number for this function, and we want to do it in a smarter way, so we can reuse some of the previous calculated results instead of calculating all from scratch again for every row and column number combination. So let's look at what's kind of a relationship between that we can have here. So just think about we have a very abstract board and we want to figure out the FRC value for a given location. So it will be really useful if we can know the values that's just one row and one column above us. Because we can just grab that value and try to look at the same row and the same column to see how many values we have on the row to our left and how many values we have above us. To determine how many rows and columns we can reuse from the square that ends as at this X location. So let's say that this is a 3. So on the board it will look like it will be looking like something like this. So when we look at the location here, it's going to be the FR minus 1, C minus 1 value. Oh, sorry, the column is shifted by 1. That value is 3 because it's bounded. There are 0 here preventing it to go up 1 level, and we have a 0 here to prevent it from, including the same story. The cup of 0 here is preventing the value of minus 1 column minus 1 to be larger than 3. But when we think about this current location, we really want to use as many rows rows and as many columns from that the square that's towards our upper left. And how many rows and columns we can utilize is determined. It's pretty much determined by the number of ones we have to our left and the number of ones to our directly above us, which we can figure that out by looking into the which we can figure out by looking at these two function results. So the row -1 column is telling us how many ones we have that's above us, and row column -1 is telling us how many ones we have to our left. And so these three combined, we can just take a minimum of these three things. That's going to be the number of rows and number of columns we can reuse from the square that's to our upper left. And to add one more row and one more column to that square, we can just add one to the length. So that's pretty much the recursive relationship. And the base case for this question is going to be so base case is going to be for the first row and first column, because it couldn't reuse anything. It depends on all by itself. So the function RC, when the either row or column is 0, it's pretty much the matrix value. So if it's a 1 there in the matrix, the square that the end at that location, the maximum one, is going to have length 1. So yeah, so this is pretty much the base case and the recursive relationship to code up this dynamic programming question. So let's start code. While we are populating the table, we're gonna keep track of the maximum. We're gonna update this maximum area with the FRC we just calculated. So initially this is 0, and we're gonna handle some edge case because nothing is mentioned here. So with the dimension here, we can populate a 2-dimensional table for storing all the values for FRC. We call it DP. Then we just enumerate over all the locations in the 2D matrix to populate the DP table. So if the matrix has a value 0 in that cell, we obviously don't care about. We don't want to do any kind of updates to the DP location because it's going to be 0 in there. Note that this is actually kind of nasty. It's a string, it's not an integer, even though it's said to be a binary. Otherwise, we will first solve the base case, handle the base case. Once the base case is handled, we can handle use the recursive relationship to handle the other situations. once we updated the new value for filled the value for this given location, we try to update the maximum area. Oh, it shouldn't be max area, it should be max length. Sorry. And in the end, we just return that maximum length squared. So let's quickly check if I'm missing anything. It looks right. So let's submit. Okay, it's accepted. So the time complexity and space complexity is quite obvious here. The space is this DP table, which is number of rows multiplied by number of columns. The time complexity, you can see that by the double loop here. So it's n multiplied by n, number of rows multiplied by number of columns. We can actually do one optimization, because when we look at the recursive relationship, all we need is the SAM row, information from the SAM row, or the row that's -1 or a column -1. So we can effectively reducing this from a 2D into a one-dimensional DP solution. So let's quickly very quickly do this. It shouldn't take much time. So we're gonna just have one row with the certain number of columns, and now it's just translating this. Actually, break this. When we are dealing with one of the new rows, we can actually create a temporary new row in there, and so that we can be clear about what value is the from the previous row, and what value is from the current row that's recently been updated. And after that row is processed, we just assign the new rows to the old row, kind of reusing that. So we effectively have two rows instead of the whole matrix. And okay, so we're gonna have a new row, which I now here call NDP. And this relationship is going to be NDP. Row column number is going to be minimum between. When we see a row -1, we're going to grab the ODP row. When we see the DP row, we're going to use the new table here, a new row here. After we process this row, we're just gonna we're just gonna override the old DP row with this current one. And this update is we should grab the value from the new DP row. So that should do it. Let me see. Did I correctly run it? Yes. No, it's not working. What is the reason? What is the reason? So if we have just one row, one column with one there, it's triggered by it's the first row, first column, and the value is not 0, so we continue. We actually resume the code. It's assigning this value to be 1, and oh yeah, I should assign this. I'm sorry. Am I covering this case? Okay. Yeah. So now it's working. Alright, so that's it for this question. So for the space optimized version, it's going to be using just that column. Sorry, the number of columns, the space is going to be reduced to from the 2D number of row multiplied by number of column to 2 multiplying number of columns. So that's a slight optimization in terms of the space. The time is still the 2 multiplied together. You can see that clearly by the nested loop here. So that's the analysis, how to derive this recursive function, transition function formula, what's the base case, and the bottom-up version of the dynamic programming solution to this question. Okay, that's it.